Welcome to another lecture of this course, Mathematics for Economics Part 1. So, we have been discussing differentiation in the last few lectures. In particular, we have been talking about higher order differentiation and different properties of differentiation. So, in the last lecture, we covered what is known as implicit differentiation and higher order differentiation. Today, we are going to deal with what is known as approximation. So, we are going to start with what is known as linear approximation, and then we shall see that there could be non-linear approximation as well. And finally, we shall end the lecture with some applications in economics of differentiation such as elasticities. We have talked about elasticities in some previous lecture, but in today's lecture we are going to deal with elasticities in a more detailed manner. So, this is called linear approximation, this particular topic. So, linear approximation or other kinds of approximations are the ways to simplify a complicated function. As we have seen, a function could be of different nature, it could be very complicated in its properties, it could be having many twists and turns, but can we simplify a function through making it a linear function? If it is a linear function, then it is very simple to deal with, properties are very straightforward. For example, if you have a linear function, then the slope remains the same irrespective of where you take the independent variable to be. The slope always remains constant if you have a linear function. So, therefore, if we have a complicated function, then we can linearize that function and then it is easier to deal with. So, we are going to start with linear approximation, and here is an example you see on your screen. Linear approximation of f is the function. About a is a particular value of the independent variable, is given by this, f(x) is approximately equal to f of a plus f prime of a multiplied by x minus a, and this approximation holds if you have x, that is the independent variable, very close to this value small a, right. So, if you are in the close proximity of this particular value of x, which is small a, then you can predict the value of the function, that is f(x), through this formula. And again, to make it clear, you have this approximately equal to sign, which means that it is not exactly equal to f of a plus f prime of a multiplied by x minus a, but it is very close to that value. And for this linear approximation to hold, it must be the case that the function f(x) be differentiable at x equal to a. So, we must be able to differentiate this function at x is equal to a, otherwise you cannot find out f prime of a, and if you cannot find f prime of a, obviously this right hand side cannot be derived. So, therefore, you cannot linearly approximate the function about a. Now, note the tangent to the graph f(x), right. f(x), suppose just imagine this to be a graph in the two dimensional plane. Now, think about the tangent to this graph at this point a comma f of a, and what is the equation to that tangent, right. That equation is given by this, y is equal to f of a plus f prime of a multiplied by x minus a. Now, why I am saying this? Why did I get this particular form of the equation to the tangent? Well, the reason is very simple. At point A, at x is equal to a, the value of the function is f of a, right. So, the slope of the function is what? It is y minus f of a divided by x minus a, right. If you have two points on the straight line, then the slope of the straight line is y 1 minus y 2 divided by x 1 minus x 2. So, we are applying the same thing, y minus f of a divided by x minus a. So, that is the slope of the function, and that is exactly equal to f prime of a, that is the slope. So, from this identity, that is y minus f of a divided by x minus a is equal to f prime of a, you will directly get this particular form. And we know that this point a, f of a is a point on the graph, right, on the tangent. So, therefore, we can use that fact, and we can use the fact that f prime of a is known to us, and therefore, the slope of the tangent is given by this. So, this is the slope to the graph of f x at point a, f of a. Therefore, when I am writing that the function is given by this, right, function is approximated by this, I am actually using the equation of the tangent to the graph at a particular point. So, it is as if the tangent is representing the function close to the point of tangency. Thus, we are approximating the curve by the tangent at a, f of a. This is what I just said, that we are trying to get close to the value of the function, right. That is what we are doing here. We are trying to get close to the value of the function by using the equation of the tangent. Okay, here is the graphical representation of that. So, here you have along the x axis you have a horizontal line, and along the vertical axis you have f x, which is also written as y. So, the function y is equal to f x in the diagram has been approximated by the tangent at point P, where x equal to a, small a. So, basically what you have a, x is equal to a at this point. So, at this point you have f of a, okay, and therefore, you draw a tangent through this point capital P, and the slope of the tangent is known to us, it is f prime of a, and therefore, we approximate the curve around this point A by using the equation of the tangent. Okay, so that is what we are doing. Now, notice if you are in the neighborhood of this point x is equal to a, then the change in the value of the function is roughly equal to the change in the value of the line representing the tangent, right, around the point A. But if you take a point very different, very far away from this point A, then this gap is rising. So, if you are taking a point here, the gap will be too much. That is why if you are in the neighborhood of x is equal to a, then this approximation is valid, but if you are far away, from this point A, then this approximation cannot be valid. Okay. So, that is the geometry of it. Now, let us take an example. Suppose f x is given, f x is equal to 1 plus 3 divided by 2 x plus 1 divided by 2 x square, whole thing to the power of half. Okay. So, this seems to be a little bit complicated function, and what I need to do is find the linear approximation of f x about x is equal to 0. So, here basically small a is given to be 0 around the point 0. Now, to do that, what we have to use is this particular form, f x is equal to f of 0, because a is equal to 0, plus f dash of 0 multiplied by x minus a, that is 0. So, this is the form we have to use. Now, here what we do not know is f dashed of 0, that we need to find out. So, this one we need to know, and f of 0, that also we need to find out, and if we put those things on the right hand side, then we are through. Okay, let us put x is equal to 0 in this particular form. If we do that, it becomes this part drops out, this part drops out. So, 1 to the power half, 1 to the power half is 1. So, you have f of 0 is equal to 1. Then we need to find out f dashed of 0, right. So, I have to first find out what is f dashed x, and then I can substitute x for 0, and I will be getting f dashed of 0. And I will get this particular expression, half of 1 plus 3 divided by 2 x plus 1 divided by 2 x square to the power minus half, whole thing multiplied by 3 divided by 2 plus x, right, because we have to differentiate the term inside with respect to x, and if we do that, I will get 3 divided by 2 plus x. Okay. Now, this is the form for f dashed of x, and so here I am just going to put x is equal to 0. So, this term will drop out, this term will drop out, this term will drop out. So, ultimately I am going to get half multiplied by 3 divided by 2, which is equal to 3 divided by 4. So, I have got everything that I need, and now I will just plug them in this expression, and I will get f x. So, f x is equal to f of 0, which is 1, plus f dashed of 0, which is 3 divided by 4, and multiplied by this x term is there. So, this is the particular expression that I needed to find out. In other words, if x is very close to 0, right, remember we are approximating around the point 0. So, therefore, if x is close to the point 0, then this function can be approximated by this particular form, and you can see that on the right hand side I have a linear expression of x, it is not very complicated, right. On the left hand side the expression is much more complicated, it is not a linear form, right, of x, but on the right hand side I have linearized it, I have made it very simple. So, that is the usefulness of a linear approximation. And actually now if you put different values of x which are close to 0, you can just put them there and you will get the value of the function, right, and so this could be very useful. Okay. Now, close to the idea of linear approximation is the idea of differential of a function. So, this will be used many times in economics. It is helpful to have a sort of discussion about this differential. Suppose you have a function y is equal to f x, which is differentiable, and suppose dx is some arbitrary change in x. So, dx is the change in x, x is the independent variable. Then f dash of x dx is called the differential of the function y is equal to f x. It is denoted by dy. So, dy is equal to f dash of x multiplied by dx. So, this is diagrammatically shown as follows. So, diagram is in the next slide. Okay. So, here you have f x function and you have taken a point x is equal to 0 here, right, and dx is some change in x. So, this portion is dx. So, here dx is positive. So, therefore, the value of x is rising because dx is positive, it becomes x 0 plus dx. Okay. So, at x is equal to 0, value of the function is y is equal to f x 0. So, which is given by this point here. As x rises by dx, the value of y goes up to f of x 0 plus delta y. So, suppose delta y is the change. So, here you have that value of x 0 plus dx, corresponding value of y is this value, right. So, the value of the function has gone up. So, change in the value of y is denoted by delta y. So, the new value is f of x 0 plus delta y. So, delta y I can straight away write as equal to f of x 0 plus dx minus f of x 0. That is very obvious. So, delta y is this much, right, this is delta y, and this is equal to f of x 0 plus dx minus f of x 0. This is what I have written here. So, delta y is equal to dy, not equal to, approximately equal to dy is equal to f dash of x 0 dx. dy is called the differential, is not the actual change in y as x rises to x 0 plus dx. So, as x is rising, what is the change in y? It is here, this is the new value of y. What is dy? dy is not that one, dy is equal to f dash of x 0 multiplied by dx. So, geometrically how we can understand that is that dy is this particular value. Okay, this is the value of dy, and this is, I have written that here also, because this value is, this entire value is f of x 0 plus dy. So, that is why I have written that dy, the differential, is not the actual change in y as x rises to x 0 plus dx, right. dx, dy and delta y are different, they are close, but they are not equal. So, what is dy? dy or the differential, it is the change in y that would occur if the function y is equal to f x continues to behave the same way as it does at x equal to x 0. So, at x is equal to x 0, there is a point on the function, this is that point, and at this point if I draw a tangent, right, this is that tangent, and if the function actually had behaved like the tangent, then the value of the function at x 0 plus dx would have been y 0 plus dy. But as we know, the function is not a straight line. So, therefore, the function's value actually is exceeding that particular value, right. If the function is linear, then delta y is equal to dy, the differential gives the actual change in y, and if dx is very small. So, you are taking x's which are in the neighborhood of x 0, then the dy is a good predictor of delta y, right, and this is again something we have referred to earlier, that in the immediate neighborhood of this particular value of x, the value of the tangent is a very good predictor of the value of the function. But if you take the x to be very different from x 0, then the value on the tangent is not a very good predictor of the value of the function if the function is not a linear function, and here the function is a general function, it is not a linear function. Okay. So, that is the idea of differential. Differential, which is given by dy, it gives you the change in y, right, around a particular point, right, it has to be evaluated at a particular point if the function behaves like the tangent at that particular point. Okay. So, that is about differentials, and here are certain rules of differentials. Okay. So, we know the differential formula is given by this, that suppose y is equal to f x, right, then dy, which is the differential, is written as f dash of x dx. So, this is the general definition, but now we can use that to get different rules of differentials. So, for example, suppose you have to find out what is d of a x to the power m plus c, where a, c, m are constants. Now, this can be actually simplified, right. So, I am just using the formula here, which is f dash of x dx. So, f dash of x is this part and dx is this part, and then I just use the power rule and I get capital A small m x to the power m minus 1 dx. That is the expression that I was looking for. And here are certain other rules of differentials. So, suppose small a and small b are constants, then what is d of a f plus b g, where f and g are functions of x, let us suppose. So, that is given by a df plus b dg, right. So, the a and b are constant, so they are coming out, and f and g are not constant, so df and dg. And in the next stage, maybe you can, if they are f and g are functions of x, then you can write them as f dash of x multiplied by dx and g dash of x dx. If you have f and g multiplied together and take the differential of that, then it becomes f of dg plus g of df. So, it is like the product rule of differentiation, and then you get the quotient rule kind of thing here. D of f divided by g is equal to, this is a ratio, in the denominator you have g square, right, which means that g cannot be equal to 0. On the numerator you have g multiplied by df minus f dg. So, these are the rules of differentials. Now, there is a composite function here, suppose. So, y is equal to f x and f itself is a function of t, f is equal to g t. Then I can use the rule of differential, what is dy, dy is equal to f prime of x dx, and I can use the rule of differential on this second function. So, dx is equal to g prime t dt. Now, I substitute this dx to here and I get the expression for dy, and it turns out to be this one, f dash of x g dash t dt, and to express everything in terms of t, I substitute x is equal to g t here. So, this is the final term I am getting, f prime of g t multiplied by g prime of t dt. So, you have a composite rule for differentials. Okay, here is an example of how to use differentials. Example, express the differential dy in terms of di for the equations. So, these two equations are given. y is equal to c plus I and c is equal to c of y. So, if you remember, this is an example of macroeconomics where y is the output of the economy is equal to consumption plus investment, and consumption function is given, it is a function of the output c of y. So, we combine these two 1 and 2 together, right. First I take the differential of the first equation, I will get dy is equal to dc plus di. From the second one I will get dc is equal to c prime y dy, and then I will use dc from here in this first expression. So, this is what I will get, dy is equal to c prime y dy plus di, and I will take all the dy terms together on the left hand side. So, dy multiplied by 1 minus c prime y is equal to di, and therefore, dy is equal to 1 divided by 1 minus c prime y, whole thing multiplied by di. And interestingly, we have seen this expression before, right. This I said that this is like the investment multiplier in the Keynesian model, okay, but there I expressed this like this form, right, dy di. Here I did not differentiate y with respect to I, right, I took the differentials and I got this expression, similar expression. Okay. We have talked about linear approximation of a function, but there could be approximation of higher orders. Suppose you have a twice differentiable function y is equal to f x, right. Twice differentiable means you can differentiate it 2 times successively. Then it can be approximated by a quadratic function at x is equal to a by the following formula, right. So, here instead of a linear function, we are approximating a particular function, but now the resultant function, that is approximated function, will be a quadratic function, that is a function polynomial of degree 2. So, this is how we are writing it. So, f of x is equal to, I am expressing it as just p of a. So, p of a is equal to f of a. So, you are evaluating the function at that particular point small a plus f prime of a multiplied by x minus a. Remember, this term was there in the linear approximation also, but now you have another term, right, which is half of f prime of a multiplied by x minus a whole square. So, from here you will get x square, that is this expression becomes a quadratic function. And again, like before, this will hold in the neighborhood of the point small a. It is not valid if you take x very far away from small a. In particular, if you take x is equal to a is equal to 0, right, the point around which you are approximating it, if you take that point to be the point 0, x is equal to 0, then the terms become little bit easier to deal with. It becomes f of x is equal to f of 0 plus f dashed of 0 x, because a is 0, plus half of f dashed of 0 multiplied by x square, right. So, it looks much more cleaner if you take a is equal to 0. Okay, here is an example. Find the quadratic expression of f x. F x is given by this about x is equal to 0. So, as you can see, this f x is kind of complicated function, because the power of 5x plus 3 is minus 2, right. So, we have to make this a quadratic function of x. Now, we first we are going to use this formula f of x is equal to, not equal to, approximately equal to f of 0 plus f dashed of 0 multiplied by x plus half of f double dashed 0 x square. So, you can see that I have to take the second derivative, which is the reason why we have to have this function to be twice differentiable. Now, the function is this. So, I need to find out what is f of 0. I take x is equal to 0, it will just become 1 by 9. Then I take the first derivative, right, f dash of x, and I am skipping some steps here. So, it will be just minus 10 divided by 5 x plus 3 whole to the power 3, and if you put x is equal to 0, it becomes minus of 10 divided by 27. Similarly, if you differentiate this once again, f dash of x, you are differentiating it once again, then you are going to get f double dash of x, which is 150 divided by 5 x plus 3 to the power 4, and again you put x is equal to 0, you are going to get 150 divided by 81. So, all these values are now going to be put here, and this is what you are going to get. It will be 1 divided by 9 minus of 10 divided by 27 x, plus there is a half here, half of multiplied by 150 divided by 81 multiplied by x square. So, if you simplify this, this becomes this expression. So, the main point that one is getting, that this particular function, which seems to be a little bit complicated because the power of 5 x plus 3 is minus 2, which is not very easy to deal with, can be approximated by this relatively simpler looking function, quadratic function of x, around the point x is equal to 0. That is very important. This is true not everywhere, but around this point x is equal to 0. Okay, now we have discussed about quadratic expression, quadratic approximation. Now, one can generalize more and approximate a function as follows: f x is equal to f of a plus f prime of a divided by, this is called factorial of 1, factorial of 1 multiplied by x minus a plus divided by factorial of 2 multiplied by x minus a whole square, plus dot 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 the last term. If one wants to have a last term here, then it will be f n a divided by factorial n multiplied by x minus 8 whole to the power n. If you have forgotten your high school mathematics and wondering what is factorial, factorial is this expression. Suppose you are taking n factorial. So, this will be n, n minus 1, n minus 2. So, the numbers are going down by 1. So, the last terms will be 3, 2, 1. So, all these terms are getting multiplied together. Now, this term on the right hand side is obviously it will be a polynomial of degree n, because the power of x is n. The polynomial on the right hand side above is called the nth order Taylor polynomial for f x about x is equal to a. Obviously, we are taking the approximation around a particular point, that point is x is equal to a. So, about x is equal to 0, that is, if you take small a is equal to 0, then this term on the right hand side becomes a little bit easier to deal with, little bit simpler. Then it becomes f of 0 plus f dash of 0 divided by factorial 1 multiplied by x plus f dash of 0 divided by factorial 2 x square plus dot dot dot. The last term is f n of 0 divided by factorial n multiplied by x to the power n. Okay. Finally, before we wrap up, here is a little bit of discussion about elasticities. What are elasticities? When the effect of price on quantity demanded is measured, one could simply take the derivative of the demand function with respect to price. So, suppose you want to find out if price changes, then how much does the quantity demanded changes. So, how much are people responding to the change in prices, how much are they buying more or buying less, right? That is what you want to find out. So, the first thing that comes to mind is that you take the derivative, right. Derivative gives you the instantaneous change in the dependent variable with respect to change in the independent variable by 1 unit. Now, here if you take the derivative, the result would be change in units demanded with respect to change in price by 1 rupee, right. So, suppose you are talking about cars. So, if the price changes by 1 rupee, how much is the demand changing? How many more cars or how many less cars are people buying? Now, here the problem is this: while for things like newspapers these may be something, it is hard to conceive that quantity demanded of houses change when their price goes up by 1 rupee, right. So, think about it, this is valid for cars also. So, if the car price rises by 1 rupee, because we are talking about Indian context. So, minimum unit of money, let us take that to be 1 rupee. So, if the car price is rising by 1 rupee, then the derivative will give you how much less cars are people demanding. Now, that will be negligible, in fact that could be 0 in fact, because people are not really bothered about change of the car price by 1 rupee, because car itself is an expensive thing. Similarly, the houses, right, these are expensive things. If the price changes by 1 rupee, you will not get any result as far as derivative is concerned, it might be 0. Whereas, those goods whose prices are not very large, for example, newspapers or let us say matchsticks, right. If the price rises by 1 rupee, that might affect the demand. So, there is a problem in this case. If you want to take the derivative, then in some cases you might get some interesting result, in other cases it might be ineffective. So, instead of taking derivative, one asks in elasticities, one asks how much does the demand change in percent if the price changes by 1%. We are not talking about units as such, we are not talking about 1 rupee or 1 pound or $1. Here one is saying that if it changes by 1%, then how much, by what percent does the quantity demanded is changing. So, in both cases, if it is the price or if it is the quantity, one is not depending on the units, one is depending on the percent. By doing this, one has got rid of the arbitrary units. So, the another benefit of doing this, apart from the fact that there is a difference between cars and cigarettes or let us say matchsticks. So, that is why you need percent rather than just units. Another benefit of doing only through percent is that now you have got rid of units. So, you can compare across countries, right. So, even if you are measuring elasticity in USA, right, the elasticity will be a pure number, it will be not in terms of pounds per dollar or something like that. In India, it could have been kg per rupees. So, you see the units, if they are there, then it is difficult to compare between countries. But since we are now talking only in terms of percentages, then it becomes unit free. Thus, one gets the price elasticity of demand measured as at a particular price. So, that is also important, that when you are measuring the price elasticity of demand, it is being evaluated at a particular price. So, it is not a general expression of how much does quantity change with respect to price. It is evaluated only at a particular point of reference. So, here is a concrete demonstration. Suppose the demand function is given by x is equal to f of p. P is the price, x is the quantity demanded. Now, suppose the price changes to p plus delta P, and since the price has changed, the demand will change to f of P plus delta P. So, what is the change in demand? The absolute change in demand is given by this f of P plus delta P minus of f of P, the new demand minus the old demand, that is the change in demand. And what is the relative change in demand? It is given by this f of P plus delta P minus of f of P divided by f of P. This is the relative change in demand. The ratio between the relative change of demand and relative change in price is given by this delta x divided by delta P divided by P, and this turns out to be this, right, P divided by x multiplied by del x divided by del P. And now I am going to just use this thing here, x is equal to f p, right, x is equal to f p, and what is change in demand? Change in demand is this. Now, this second term here is nothing but the Newton quotient. F of p plus del p minus f of p divided by del p here is the Newton quotient, which approaches the derivative of the demand function at p as delta p approaches 0, right. So, change in the price you take that as small as possible, delta p approaches 0. Thus, the elasticity becomes this p divided by f of p multiplied by dfp dp. So, this is nothing but the derivative of the demand function with respect to the price. So, here is a concrete example. Find the price elasticity of demand of the good whose demand function is given by this. So, as you can see, f p is a function of price, 2000 multiplied by p to the power minus 0.5. We are going to use this particular formula. For that, I need to find out what is the derivative f prime p, and this is by using the power rule, this turns out to be this minus 1000 p to the power minus of 1.5. So, I put this in the elasticity expression, and if I simplify this, actually it becomes a pure number minus 0.5. So, it no longer remains a function of p, it is a simple number minus half. So, in this case the price elasticity of demand is constant, but I must caution that this is not a general case. In many cases it could be a function of p. It does not change with the price level. As price rises by 1%, quantity demanded falls by half a percent. That is what it means. Minus half means if price rises by 1%, quantity demanded falls by half a percent. Now, this is the general notion of elasticity. So, if you are just ignoring the fact that we were talking about only price elasticity of demand, there could be a general notion of elasticity for a function f x, right, it is a function of x. The elasticity with respect to x is given by, suppose this E of f x is x divided by f x multiplied by f dashed of x. Okay, here is an example. Suppose the demand function of a good is given by d of p. So, the revenue earned means total amount of money that the sellers are getting is p multiplied by quantity demanded, that is p multiplied by dp, and if you take the derivative of rp with respect to p, you will get this expression, right. So, I am going to skip some steps. You can show that this particular right hand side you can get it if you take the derivative of this with respect to p and use the formula of price elasticity of demand, which has been used here. Therefore, ERPP, that is the elasticity of the revenue with respect to price, is given by this particular expression, right. I am just using this particular formula here, and now you simplify this by using r prime p is given by this. So, I am substituting this here, right, And what is Rp? Rp is P multiplied by dP. So, P will get cancelled. So, you are going to get 1 divided by dP multiplied by dP multiplied by 1 plus elasticity of demand. So, dP will cancel, and therefore, the elasticity of revenue with respect to price is given by 1 plus the EFP. What is EFP? It is the price elasticity of demand. So, as price rises, whether the revenue falls or rises depends on if the price elasticity of demand is less than -1 or greater than -1. In the former case, that is, if the price elasticity of demand is less than -1, then this whole expression becomes negative. So, therefore, the revenue falls as the price rises. And if it is the other case, that if it is greater than -1, then the latter rises, that is, the revenue rises as the price rises. If there is no change in the revenue, if the price elasticity of demand is exactly equal to -1, in that case this right hand side becomes 0. So, as the price rises, the revenue does not change at all. And we are going to end with some rules of elasticity. So, if you take f multiplied by g and take the elasticity of that with respect to x, you are going to get EFX plus EGX. So, it is the sum of the elasticities, and if you take the quotient of them, E of f divided by Gx, then it is the difference of them, E of fx minus E of Gx. If you take the summation of f and g, then it becomes a little bit complicated expression, f of E fx plus g of E Gx divided by f plus g, and similarly if you take the difference, it becomes this expression. Now, we have talked about own price elasticity before. So, you take a quantity demanded and you change the price of the same good, that is called own price elasticity. Now, there is something called the cross price elasticity also, which is, suppose price of some other good changes, then the quantity demanded of a particular good can change. For example, think about tea leaves and let us say sugar, right. If the price of sugar changes, it is conceivable that the demand for tea leaves can change. So, we can measure that also. So, this is given by E of dx py. Here the price and the quantity are two different goods. You can find out income elasticity of demand also. If income changes, what is the change in the quantity demanded, right, and that is called income elasticity of demand. And all these things were from the point of view of demand. There could be elasticities from the point of view of supply also. So, as the price changes from the supplier's point of view, how much do they respond to that, right, that is called the price elasticity of supply. So, this is given by E of Sx Px and so on. There could be many more other kinds of elasticities that one can explore. Okay, I think we shall call it a day today, and I will see you in the next lecture. Thank you.